Okay, so a couple of more items left here. Black carbon. You hear about it a lot, especially in the context of health impacts, which is pretty massive. It is a contributor to global warming as well. You can compute its carbon footprint at 7 to 15 billion tons of CO2 equivalent per year. That is 15 to 30% on top of the figure I normally quote for global human-made emissions. There are a few things to remember. Black carbon obviously absorbs solar radiation and has obviously has global warming potential. And it can fall on snow and ice and glaciers and absorb radiation in them and accelerate their warming, their melting, and reduce the reflectivity as well. And add additional global warming that way, change the energy balance. But the story is actually quite complicated. It has a very short residence time, as we will see in a minute, and there are some studies that argue that removing black carbon, because of the way the atmosphere quickly responds to black carbon versus sulfur dioxide and sulfuric acid that forms when the sulfur dioxide dissolves in atmospheric water, vapor and water. There are some radiation calculations that argue that the contribution of black carbon mitigation to global warming will not be great. On the other hand, one can hardly argue the improvements in health you will get by removing black carbon. Okay, so this is a nice infographics from Climate and Clean Air Coalition, which puts out very nice infographics on many things like black carbon, methane, N2O, and so on. So the sources: black carbon is one of the many particles and gases that are emitted when diesel, coal, and other biomass fuels are burned. You remember we saw that a large part of the world still burns biomass for cooking and so on. So household energy 51%, transport, agriculture, industrial production, waste, fossil fuel operations, and large-scale combustion, including forest fires and so on. Black carbon or soot is part of the fine particulate air pollution PM 2.5, which can directly go into your lungs, into your bloodstream, into your stomach, even in the brains of humans and street dogs and so on, and is reported to produce serious problems. And of course it contributes to climate change as well. So the deaths from health, so 7 million pollution-related deaths every year. These are premature deaths because they are caused by impacts of the air pollution. So heart disease, stroke, lung disease, and lung cancer. So climate absorbs black carbon absorbs sunlight and converts it to heat. Lifetime in the atmosphere is up to 2 weeks. Snow and ice accelerated melting prevents clouds from being formed because it absorbs sunlight and is not a good cloud condensation nuclei. It also alters regional weather patterns and rainfall. Agricultural ecosystems, agriculture and ecosystems. Black carbon can reduce sunlight and affect plant health and productivity. Some key figures from CCAC. Black carbon has a warming impact on climate of 460 to 1500 times stronger than CO2 per unit mass. So its global warming potential is massive. 460 to 1500 times CO2 per unit mass. Okay, it's typically done over 100 years of forcing at the same mass. 4 to 12 days is the average atmospheric lifetime of black carbon particles. 6.6 million tons of black carbon were emitted in 2015. 51% is the household cooking and heating that accounts for black carbon. Black carbon emission trends. Latin America, so you can see there are various categories here that I won't go into, but in general there are some that are decreasing, there are some that are increasing, so you have to be careful about the net what's happening here in East Asia, Southeast Asia, and Pacific. All the numbers are negative, but it's a relative change. Percentage of change from 2000 to 2015, projected percentage change from 2015 to 2030, and the blue one is projected percentage change from 2015 to 2030 under mitigation scenarios. So mitigation of black carbon and short-lived pollutants is generally recommended as one of the key solutions because the impacts will be quite immediate. If you make mitigation efforts towards reducing black carbon, you will see the impact literally in a week or two. Of course, quantifying health impacts will take longer and so on. So awareness is high, and black carbon is a problem for sure for health and for all these things we looked at, but exact mitigation impacts on warming is something else that is debated. Okay, let's look at the annual emissions of humanity as a whole. This is annual CO2 emissions from the burning of fossil fuels for energy and cement production. Land use change is not included in here. So this is going basically from industrial revolution through to almost the present, and you can see that we have super exponentially increased the total number of CO2 emissions just from fossil fuel burning and cement production. Land use can be a negative or positive depending on where you are. The global mean is definitely positive. Deforestation, urbanization, and loss of wetlands. Nowadays, permafrost thawing is another thing to worry about. But always try to see whether it's being expressed as carbon, CO2, or CO2 equivalent. The numbers can be different. So here we were in 2019 at just under 40 billion tons per year. Total greenhouse gas emissions. So now greenhouse gas emissions from carbon dioxide, methane, nitrous oxide, and flue gases are summed up and measured in tons of carbon dioxide equivalents, where equivalent means having the same warming effect as CO2 over a period of 100 years. So we have to convert using global warming potentials. Emissions from land use, which can be positive or negative, are taken out. Okay, so here this is going from 1990 to 2016, and you can see that this number is larger than here because now you are including methane, nitrous oxide, and flue gases as well, and land use is still not included here. Okay, so it's worth looking at sectoral emissions as well. This is, I think, from 2016 here. That gives you a sense of where the highest mitigation potentials may be. So energy as a whole is almost 3/4 of the human emissions, and it includes energy used in the industry, the iron and steel, chemicals, food and tobacco, paper, pulp, machinery, and so on, and other industries, transportation, road, aviation, shipping, and rail, and energy used in building, commercial and residential buildings. And then you have these other sectors here: unallocated fuel consumption, fugitive emissions from energy production, flaring, etc., energy in agriculture and fishing. Cement is always something to worry about. Chemicals, wastewater, landfills, deforestation. So agriculture, forestry, and other land use, or AFOLU as it is referred in short form, contributes more than 18% here in 2016. Okay, so this gives you a sense of where mitigations can happen. Global greenhouse gas emissions by gas: carbon dioxide is of course most of it, methane is 17.3%, flue gases, HFCs, CFCs, and nitrous oxide. So we have to worry about not just the concentration, but residence times and their global warming potential. Methane, for example, lasts for only about a decade, and N2O, I think, lasts for a couple of centuries, and carbon dioxide can hang around for a very long time, multiple centuries as well. Flue gases, it depends on which one. Some can last for very long, some are very short. Okay, so we do need to look at global warming potential because we have mentioned it several times, and I've always explained it verbally. Global warming potential of greenhouse gases over 100-year time scale, that's referred to as GWP 100. Global warming potential measures the relative warming impact of one unit mass of a greenhouse gas relative to carbon dioxide. A GWP 100 value of 28 therefore means 1 ton of methane has 28 times the warming impact of 1 ton of carbon dioxide over a 100-year time scale. So you maintain both of them at the same mass. These figures do not include climate change feedback effect. So the feedback of CO2 onto radiation, vegetation, ocean uptake, ocean acidification, coral loss, etc., and methane's impact on various things can be very different. So that complicates life quite a bit. So people also argue that it shouldn't be done by mass, but should be done by molecules, but we have to do something. So SF6, 23,500 times CO2, PFC 14, nitrous oxide, HFC 152A, methane 28 times, carbon dioxide is of course our scale of 1. So again, residence times matter and global warming potentials matter, even though we are always comparing them at a 100-year time scale forcing. Okay, so no good news there. COP26 has just started today, Monday, and expectations run high, but let's see what comes out of it. Many countries are submitting their net zero plans, and already a British advisor criticized Australia's net zero plan as unrealistic and not credible. So countries will announce, and countries are under pressure to announce net zero plans, but this is a promise out into the future. So whether we call it net zero or decarbonization or emissions reductions, if you look at the CO2 emissions globally, there is no dent at all despite the 25 years of negotiations. So keep those things in mind. Okay, so we are pretty much not going to meet the 1.5 degrees C global warming target by any means. 2 degrees C maybe, but there are very high expectations of reliance on carbon capture, utilization and sequestration, which is still not available at scale. Not any technology that exists for CCUS does not draw down enough carbon to have any kind of hope for relying on them as a part of the net zero solution. Okay, bad news, but that's the reality.